Sense embeddings represent one of the smallest linguistic units in NLP. And for sure, they represent the smallest meaning unit that we are going to study in detail in this tutorial. But what are sense embeddings? This is actually not an easy question to answer, because even the question of what are senses is somewhat controversial, and different researchers will answer differently. So why we need to model senses, or what they are, what is meaning, what is the meaning of a word? These are the kind of questions that we are going to try to answer in this tutorial. And not only that, but of course we are going to move into details, into the main modeling techniques that exist to learn vector representation from senses. This is the outline of this presentation. We are going to start with to define the meaning completion deficiency, because this is one of the single main reasons of why sense embedding exists and why we maybe need to bother for modeling senses. Then we are going to move to explain the different paradigms in sense representation learning. That is unsupervised, whereas usually you need only a text corpus to learn sense representations, and knowledge base, where the goal is not only to improve sense embeddings by using knowledge or lexical resources, but actually it is also to link them into lexical resources. So this is a completely different paradigm. And finally, as usual, we are going to explain the main applications and some common evaluation procedures. To understand why we need sense embeddings, let's go back to word embeddings first. One of the limitations of word embeddings is that they cannot capture ambiguity, at least not in an explicit manner. For instance, the English word bank, it can have two different meanings. One, it can be the financial institutions, what we can have here on the left, and on the right we have here the geographical meaning, that it can be the bank of the river, for example. This may be problematic if you have a representation that doesn't take into account that two different meanings and distinct types in this case exist. So let's see a graphic example first. Here we have the word bank that is here in the middle in a word vector space. So this is just a common word embedding model. In this case it's word2vec, where you represent bank there in the middle of a sea of words. And let's see here, let's zoom in for a moment. So we have here a cluster, the red cluster and the blue cluster. The red cluster, if we zoom in a bit more, we see that we have words like finance, banking, monetary. So clearly we are talking about the financial institution meaning of bank. But here, in the other side, we have something like canal, quay, blue water. I mean, words that give you an intuition that you are perhaps in the geographical meaning of bank. And if we go back, we see here that the word itself, bank, was kind of in between both of them. So it's not in one cluster and not in another one. And obviously this may be problematic, even if you have some kind of representation in your vector space or in your word representation of the two meanings. Let's go for another problem that word embeddings may have, that is a triangular inequality. So as we know, in word embeddings, what we want is like similar words are going to be close in the vector space. And here, for example, we have pollen and plant, that obviously they are very similar, because we have the biology meaning of plant and pollen that we know they are quite related. And then we have the industrial meaning of plant that is obviously very close to refinery. So what happens here? Because we have the triangular inequality, this is something that will pull together pollen and refinery. So because pollen and plant are very close and plant and refinery are close, it ends up that pollen and refinery are also kind of close in the vector space. But ideally, at least intuitively, we will want something like this. So we have pollen that is very far from refinery because they have nothing to do, but is very close to one meaning of plant. And the same as refinery is very close to the second meaning of plant. But of course they are not close to each other, no? So there is a long distance between the two senses. And here, obviously, the triangular inequality holds, and there is not nothing that will lead us think that something is not fulfilled. This is one of the limitations. There are others. A very common one is like they neglect usually their senses, because they are usually based in a word corpus. Most of the word embeddings, they tend to capture the meaning of the most frequent sense. So for example, in bank, if you have a general corpus where you are talking about banking or different things, obviously you are going to completely neglect the geographical meaning of bank. And this is obviously problematic because for language we know that even if we are not going to use very often, if we are in some application, we will need to use that sense. So this is another of the motivations of why we have senses. So what is the goal? The goal is to represent senses and not words. In this case, so we have our example of bank again, that is in the middle of the word vector space. So what we want? So we want actually to have two representations, one for the financial meaning of bank and another one for the geographical meaning of bank. And how this translates into application or into natural language. So we have here the sentence, no? He withdrew money from the bank. Bank has two meanings, as we saw. One is the financial meaning and the other one is geographical meaning. So here, obviously, if we have this context, we will want to use the financial meaning of bank because this is the meaning that is triggered by this sentence. And here, obviously, I had to mention the contextualized word embeddings that are actually very relevant in this area. And they are very popular nowadays and one of the most trendy applications in NLP. For this, I would refer you to the next video. So here we are going to focus more, let's say, like in a static sense embeddings. But if you want to know more about contextualized word embeddings, I recommend you to see the next video. What kind of sense embeddings there are there? So we have two different paradigms, as I mentioned in the introduction. First is unsupervised, where you just need a text corpus and then the model decides itself what is the sense and also the vector for that sense. And knowledge based. And here, as I mentioned, the main difference with unsupervised is like senses are linked to knowledge resources. And it is not like they don't use text corpora, as most of these approaches also do. They use text corpora and take into advantage of the knowledge that is present in lexical resources. And then these senses are linked into these resources. So let's start with unsupervised sense embeddings. We can divide unsupervised sense embeddings in roughly three main approaches. That is clustering based, or what is also commonly known as two-stage models, joint training, or sense embeddings that actually are learned from multilingual corpora. Let's start for the first one, clustering based. This is the main approach. So how it works? First, as I say, you have a large corpus where you have many different sentences for where a word occurs. Then what you want to do is try to analyze those contexts and cluster the different contexts. Here, for example, in different colors. Like here we have the orange one, then we have the blue one, where actually represent different meanings. Like for example, this first one that is yellowish one, you are representing the biological meaning of cell, and accordingly, then you can learn this representation. And for this, actually, you can use even common word embedding methods to compute this sense representation. The only thing that you need to do first is try to cluster the sentences by their meaning. And obviously, for this, there are many different ways to do that. The second kind of approach is joint training. These methods, what they do is learn and cluster the senses simultaneously. So they are not two-step process where once you cluster the words by meaning and then you learn the representation. As I mentioned, in those kind of approaches, you could use, for example, common word embedding approaches. So here actually you have that advantage that you don't need the two-step process, and both of the processes can benefit from each other. Here also I had to mention that in most of these approaches assume a fixed number of senses per word. That can be problematic. But that is not the case in always, as there have been also recent approaches that they take into account this by dynamic polysemy. So this is also one of the parameters that is going to be learned by the model. And finally, we have other type of model, what we call pure sense-based models. Because before, as I show you in the figure, what you did is you can try to disambiguate one of word in context, but you're not going to disambiguate all words in context. So these pure sense-based models, what they do is everything is going to be sense-based. So you are not going to disambiguate only your target word, but all the words in the sentence, or at least all of them that for what we want to learn as sense representation. And this is what we call pure sense-based models. And finally, we can learn also sense embeddings from multilingual corpora. Obviously, this is not the same that using just monolingual corpora, and has its advantages and disadvantages. Obviously, one of the disadvantages is that actually you need many of the times like parallel corpora, or at least corpus that has been translated into other languages. So here, what is the main idea? The main idea is like in different languages, we can represent senses differently. So different senses of the same word, maybe they are translated into different words in another language. So here we have the example of the English word crane, that is very ambiguous and have two unrelated senses. That one is bird and the other was the machine. So for example, you translate English to Spanish, you have these two different words that you translate into grulla or grua, depending on the context. And this already gives you a hint that maybe grulla and grua, they represent two different senses. And maybe in English, the English word crane, that has two different senses. So then, if you have a parallel corpus or a translation of a corpus, you can simply take into account and then learn the representation for these distinct senses. And obviously, the more language that you have in your parallel corpora, because you can have two or you can have more, the more hints you have that maybe you have different senses. So this was a very brief overview of unsupervised sense embeddings. Of course, we gave references if you are more interested in those. And then we're going to a short overview on the knowledge-based sense embeddings and what are the main differences with the unsupervised sense embeddings. So the knowledge-based sense embeddings, of course, they make use of what we call knowledge or lexical resources. Some of the more common ones are displayed here, like Wikipedia, BabelNet, Freebase, Wikidata, and WordNet. Obviously, here we are merging like encyclopedic dictionary or encyclopedic resources with more dictionary-like resources like WordNet. And obviously, the approaches will differ, depending on the resource that you want to use. Here, we're going to focus mainly on WordNet, that has been the most popular source to learn sense embeddings. And I'm just going to briefly explain what is WordNet for those of you that don't know. So WordNet is a lexical resources when you have where you can see first as a dictionary. So you have words and you have different definitions of each word. Obviously, each of the definition of that word is what we are going to call sense. And like what you call in WordNet, what you're going to call synset. So a synset is actually one of the circles here that we have in this image. So here, for example, we have the synset of plant, and plant then is connected with all the different synsets like house plant or organism being. So this is a hypernymy relation or an ICA relation, and this is a hyponymy relations. So then you can see WordNet first as a dictionary, but you can see also as a semantic network where these different concepts or entities are linked together. So then what we want with sense embeddings. So here, for example, we have the word plant, and we have the different meanings of plant. We have 4 different plants here. As we say, the industrial plant and plant in the biology sense, for example, among others. So what we want is simply to have a vector representation, not for the word plant, but for each of the entries in this dictionary, let's say, in WordNet. How are we going to do that? There are many different approaches on how to do that. A common approach is, first, we are going to take our underlying resource. So in this case, for example, WordNet, but it can be other, as I mentioned before. And you are going to have all the meanings of one particular word. For example, we have a running example cell here, where you have the jail cell, or the biology meaning of cell, or cell as a cell phone as well. It can be. So you are going to do this first, and then you are going to try to gather information somehow for each particular sense. And here is where most of the approaches differ, because this information you can maybe exploit the semantic resource, like a WordNet as a semantic network, or you can exploit its definitions, or you can actually use text corpora as well, as many approaches do. And finally, you are going to compute the sense representation here, for example, for the 5 meanings of cell. So in this case, for the 5 senses of cell. So what are the main sources of information? There are more, and as I mentioned, you can use also text corpora, but the main different sources from models is two: is definitions and semantic network. And then there is also some approaches that try to combine the two and try to get the best of both worlds. So with definition, simply, as a human, once you get a definition, you can more or less understand what the word is about. So that is what you're going to try to fit to the machine as well, to model that sense. And as a semantic network, is also simple. So as I mentioned before, you have maybe is-a relationship, domain relationship, and having all this huge graph, because they are going to be, if we are going to model a resource like WordNet, it's going to be a kind of a big graph. You can develop different methods to infer the meaning of the word and actually to create a vector representation. That is what we want. And here also, if you are more interested, you can check the video on graph embeddings, where there are some information on how you can do this, and some of the common methods to actually learn representations from graph or from semantic networks. And finally, as usual, we are going to see the main application usages of sense embeddings and how we can evaluate them. The main motivation of why we're having sense embeddings is actually to integrate them into downstream NLP tasks. So the idea is that having sense embeddings and this finer granularity, we can improve end tasks. Obviously, the integration of this additional knowledge of these sense embeddings is not trivial and often requires what is called word sense disambiguation, where the idea is actually to find the most appropriate sense in context. At the same time, sense embeddings can also help with this word sense disambiguation process and be useful in other direct applications such as similarity, where you can easily integrate these sense embeddings. And as we have been repeating throughout this tutorial, one of the main motivations why we want to have a vector representation is because they are very practical, especially when they are low dimensional. And you can integrate into many different applications. One of these use cases can be, you can use sense embeddings to improve lexical resources, as this representation can give really an important clue in applications such as clustering, retrieval, or any kind of tagging that you want to do in your lexical or knowledge resource. And finally, how can you evaluate sense embeddings? There are many different ways where you can evaluate them, but most of the times, as it was argued with word embeddings, you try to evaluate it in extrinsic tasks, so how can they be useful? But at the same time, there are also some benchmarks that are intrinsic and lexical semantics tasks, also related with similarity, and different tasks where you can actually try to make a sense of how these sense embeddings work and some of their intrinsic properties.